Let's imagine that you have a positive and decreasing sequence, kind of like this one. Another way to think about the summation of this sequence is to imagine you're adding rectangles of width 1 and a height, the value of the sequence at that end value. So here is the first rectangle, and this area has a value of A1. And here's second rectangle, so width is also 1, so this area is A2, and so on and so forth. Kind of like this. And this is one way you can visualize the addition of every term in the sequence to infinity. But doesn't this look a little familiar? This looks a lot like integration, where if we have a continuous curve following this path of the sequence, then we could also take the area under the curve and we would get a similar result. But the difference is the sequence is discretely defined. That is, it's only defined at integer values of the first term, second term, third term, and so on. But this curve here, which I'm just going to label f of x and lay over the graph of the sequence, is defined at every point on the x-axis and just so happens to have the same value as the sequence at every integer input. So because the curve and the sequence have the exact same outputs at every point in the sequence's domain, we can say that the sequence of n is equal to this function of x. So now remember back to when we were adding rectangles as a visualization of this sum. Well, if you notice, the area under the curve of f of x encapsulates all those rectangles plus a little bit more that we missed. So because of that, we can make the conjecture that the integral from 1 to c of f of x dx will always be greater than the partial sum for c terms of the sequence. And since we established that this sequence is positive and decreasing, we also know that this must be greater than 0. Now, look what I'm going to do. I'm going to take the limit of all three of these as c goes to infinity, like so, and we can condense this into this. So we've learned how to solve quite a lot of integrals, including things like this. However, we haven't learned how to figure out very many series yet, so we're going to use this relation to our advantage. So we're going to say that if this is finite and 0 is also finite, then by the squeeze theorem, this series also has to be finite or convergent. We can also say that if the result of this integral is infinite, then the result of the series must also be infinite or divergent because both a of n and f of x use the same values. This is called the integral test for series convergence, and formally it reads, if f of x is positive, continuous, and decreasing for all x's greater than some c, and f of x equals the sequence, then the behavior of the infinite series and the infinite integral are the same. And notice that we have a general constant c here. That means we can start the series from anywhere and the integral test will still work. I'm going to do 3 examples for you using the integral test. The first up is the series from 4 to infinity of 1 over n. So first we have to find the function f of x that correctly models the series 1 over n. And all we do is just replace the n with an x. So our function here is just 1 over x. And by the way, that's all you have to do to find the f of x. Just take these n's, replace with x, and you're good. And we know that 1 over x is positive, decreasing, and continuous, so we can apply the integral test. So I'm going to be integrating from 4 to infinity of 1 over x dx. First, I'm going to make this integral proper with a limit, like so. And we know that this integral is equal to ln of x, like so. And we're evaluating from 4 to b, which expands to this. So ln of 4 is a constant, but ln of b, when b goes to infinity, is ln of infinity, which is infinity. So this integral diverges, so this series also diverges. Now our second problem is the series from 1 to infinity of 3 over n plus 2 to the 4th power. Like last time, I'm going to begin by finding our f of x, and very simply, I'm just going to replace n with x, and that's our function. Now I'm going to find the integral of f of x from here 1 to infinity, like so. And I'm going to begin by, again, using the limit to make the integral proper. And now I'm going to pull the 3 out of the integral, like so. And now I'm going to perform a substitution, and I'm going to let u equal x plus 2. And differentiating, we find du equals dx. So our integral turns into 3 times the limit as b goes to infinity of integral from x equals 1 to x equals b of u to the minus 4 du. And using the power rule, we get this. And now I'm going to rewrite and substitute for u, like so. And then we're going to evaluate from 1 to b, like so. And notice that When we take b to infinity, this denominator also goes to infinity, making this fraction 0. And that just leaves us with this. And since this is a constant, we can just drop the limit, and our final answer is 3/81, which is equal to 1/27. So this integral converges to a finite value. This series must also converge. And lastly, we're going to see if the series of ln n over n is convergent. So I'm going to get my function of x, which is simply ln x over x. And now I'm going to integrate from 2 to infinity of ln x over x dx. And as always, I'm going to make this integral proper with a limit, like so. And you'll notice that I've rewritten the integrand, and this is for a reason. We're going to let u equal ln of x. So du equals 1 over x dx, and conveniently we have 1 over x dx. So our integral is now the limit as b goes to infinity of the integral from x equals 2 to x equals b of u du. And using the power rule, we get 1/2 u squared evaluated from x equals 2 to x equals b. Now I'm going to substitute back for u, like so. And now I'm going to evaluate from 2 to b, like so. And you notice that when b goes to infinity, ln of b goes to infinity. So making all this infinity, which makes this integral divergent, which also means the series here must be divergent. And that's how you use the integral test for convergence. By the way, since the integral test is really tedious, I would save it as a last resort in case the other tests we learn later fail.